Raw query logs hide repeated user intent. HDBSCAN turns messy queries into clusters you can actually inspect and improve. This is the setup you'll be able to run after this, which clusters recurring search queries and highlights density signals for prioritizing fixes. I'm Professor Pi, teaching search and IR with simple Python. Search logs record everything users type, but they rarely type the same phrase twice. Small wording changes scatter the same intent across many rows. That makes it hard to prioritize fixes, detect popular issues, or measure demand. Query clustering takes those raw lines and groups them into coherent intents you can act on. HDBSCAN is a density-based cluster that works well when clusters have irregular shapes and you do not want to pick a fixed cluster count. It finds dense neighborhoods of similar queries and marks sparse queries as noise. In practice, that means fewer false merges and nicer, human-readable groupings you can inspect. The intuitive idea is simple. Turn each distinct query into a vector that captures its words. Where vectors crowd together, you probably have the same user intent. HDBSCAN scans that vector space and extracts the dense patches. Strong patches map to actionable intents. Isolated points are likely one-offs. We will build a small pipeline that reads a handful of search events, groups identical strings, vectorizes those queries with TF-IDF, runs HDBSCAN to get cluster labels and confidence, then summarizes clusters by session demand to pick a priority backlog item. You will see how fragile raw counts get fixed when phrases collapse into shared clusters. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, let us load some raw events and sanity check how the literal strings distribute across sessions. This snippet loads a handful of raw search events into a pandas data frame, so we can sanity check the distribution. Each tuple in the records list captures timestamp, session, and the exact query phrase pulled from the log. Pandas assembles those rows into DF, giving us a tabular baseline that the later steps can enrich with embeddings and clusters. The counter quickly tallies literal string matches and most common surfaces whichever phrasing appeared most frequently. That printed leader makes it obvious how easily near duplicates fragment intent tracing when we rely on verbatim strings. Seeing this flat ranking sets the stage for clustering to reveal cross-phrase patterns. Now we need numeric vectors so the clusterer can compare queries by meaning, not by exact text. This example groups the raw queries into unique rows and derives vector representations with scikit-learn's TF-IDF. IntentDF rolls up DF by query text, counting how many sessions and total searches map to each phrasing so we retain demand signals. TFIDF vectorizer builds a vocabulary of unigrams and bigrams. Then fit-transform produces the sparse matrix query matrix. Converting that matrix to query vex keeps a dense float32 array ready for downstream clustering without extra casting later. The printed count confirms how many distinct query forms remain after grouping, ensuring we have appropriate granularity for intent discovery. A higher n-gram range would expand vectors and highlight longer phrases, while a smaller range would emphasize individual tokens. With vectors ready, we can let HDBSCAN find dense groups and label queries that fall into noise. This code applies the HDBSCAN library to those vectors, so similar queries collapse into shared intent clusters. HDBSCAN initializes with min cluster size equals 2 and min samples equals 1, matching our expectation that at least 2 related searches should support an intent. Setting cluster selection method equals leaf, favors fine-grained leaves in the hierarchy, which is useful when short strings would otherwise merge too aggressively. Fit links the geometry of query vex to the density model and exposes integer labels for each query. The set comprehension counts how many cluster IDs are non-negative, ignoring noise so the print reflects actionable groups. Raising min cluster size would require higher evidence per intent and likely reduce clusters found. Lowering it would admit noisier pairs. Labels alone are raw. Next, we combine them with session counts and cluster confidences to see what matters. This snippet enriches the grouped queries with HDBSCAN outputs and ranks clusters by the combined session demand. IntentDF receives the raw labels plus membership confidence, keeping the clustering metadata alongside query text and counts. Filtering to non-noise rows before the group by ensures we summarize only actionable clusters. The aggregation tallies how many distinct queries sit in each cluster, sums their session coverage, and averages stability so the table mixes scale and reliability. Sorting by sessions exposes which consolidated intent has the widest user reach right now. The printed total spotlights the top cluster's session count, clarifying why that intent deserves the next diagnostic deep dive. Finally, we select one strong representative per cluster to make a tidy prioritized backlog item list. This example turns the cluster summaries into a prioritized backlog by selecting the strongest representative query per intent. Multiplying sessions by confidence yields weighted sessions, capturing how much trustworthy evidence backs each phrasing. After sorting on that metric, the group by and head 1 pattern keeps only the top-ranked query for every cluster while dropping the rest. Resetting the index produces a tidy priority table that analysts can feed into review workflows or ticket templates. The printed query reveals which concrete phrasing should anchor the next round of debugging or relevance fixes. If you tighten the confidence threshold earlier, the same pipeline would focus the backlog on only the most stable clusters. On a real product, you would run the same pipeline over daily logs, store cluster IDs with queries, and surface the top clusters to the relevance team. That gives a short list of concrete phrasings to test, fix, or write synonyms for, driven by real session volume. Query clustering groups similar search phrases into shared intents, so you stop chasing verbatim noise. Use this when you have messy logs and want prioritized, demand-driven fixes instead of long-tail manual sampling. Remember one caveat. Density clustering depends on your vector features and min cluster size, so tuning affects how conservative or aggressive grouping becomes. Next step, swap TF-IDF for dense sentence embeddings and rerun HDBSCAN to see whether semantic embeddings produce tighter, more recall-focused intents. If practical IR and clean backlogs help you ship better search, subscribe and watch the rest of the IR videos.